Okay, it's recording. All right. So, um, welcome everyone to the PhysClub student seminars ran by PhysClub and our very generous librarian who came here. Um, so yeah, this talk is going to be on string theory. Why did I choose this topic? Well, I like giving talks at the student seminars ran by PhysClub, and I usually give at least one talk every term. I decided to give a talk this term. Me and my supervisor are writing a paper together, and we thought it would be published before um, March 28th, which is today. So I thought I would just give a talk on that. But things happened, we got busy. We haven't finished the paper yet. So that's why I couldn't talk about that. So I needed to find a last minute replacement for the talk because I already signed up. And I said, what should I choose? I should choose something that I can learn in a week because when I was deciding this, the talk was in a week. So it should be something easy enough that I can learn in a week, and also interesting enough that people care about. I was initially thinking of giving a talk about manifolds with corners, but even my pure math friend, who's an algebraic topologist, said even now I find that boring. So I said, yeah, fair enough. Let me choose something else. So I chose one of the hardest things you can learn, which is string theory. For some reason, I chose it at 3 a.m. So maybe that's why I made this choice. Um, so then I had to pick a resource where to learn string theory from. Um, the resource I chose was Leonard Suskind's Stanford Lectures on string theory. They're on YouTube. Just look up Leonard Susskind String Theory Stanford. Should be the first thing. It's a playlist of his lectures on string theory from Stanford. And I was looking some other resources. They all looked very difficult because, well, string theory, the nature, it's just the nature of the beast is very difficult, notoriously so. And those lectures seemed more introductory friendly and less intense. So I picked those. I was going through them, and I I would definitely wanted more math. And those lectures don't contain a lot of rigorous math, I would say, at least not as intense as some other courses on string theory or how string theory is done in a modern version. And just so you know, this lecture is being recorded, so I hope you guys are okay with that. The first three rows are in the camera. The camera can see the first three rows, but not the last two. So just so you know. And yeah, so I like string theory. I was going through the lectures. I wanted more rigorous math, but something one fact was that in terms like those, when because it was a last minute decision I made, you can't really change your what you're going off of, because if you keep doing that, then you won't get to cover anything in time. So I just choose to stick with that resource. And something I realized is that it might be a good thing because I was expecting a lot of like second year or third year physics students to be attending this talk. And maybe the very intense string theory would scare off a lot of people because of the very advanced math. So maybe this is more friendly to people who haven't seen all that advanced math. So maybe it's a blessing. I hope it is, because that's what I decided to go off of. And there's no set time for these student seminars, but so I thought maybe a reasonable thing to do is I'll just keep lecturing as long as I have material or as long as you guys have interest. So I'll finish the talk when either one of these ran out, either your interest or the material I prepared. How does that sound? Do you guys want to have like a fixed time for this? Like, do you want to finish at some time? I don't know, like 8 or what would you prefer? Because I can keep going as long as I have material. I have like 15 pages ready, so that's quite a bit. And this is the first 4 lectures of that series, so I don't have anything prepared beyond that. Just one other thing that I just wanted to talk about why string theory good, how is it right, how is it correct, that I got from a different resource that I'll cite when I get to that. Do you guys think that's reasonable to just keep lecturing as long as you have interest, or do you want to set time?
I mean, we have the room until 9, but I think just from experience, most people's patience runs out like after 2 hours max, so 8.
Yeah.
But I mean, we'll see as you go along.
Yeah. Who knows? Maybe people still want to stay here after 9, and probably no one booked here after that. And I would definitely love to stay. But yeah, if people start leaving and I see the numbers diminish, of course I'll end it. So you guys won't miss too much. But yeah, any other opinions?
I personally have to leave by like 8:50, 9.
Okay.
I mean, that still gives you 2 hours 40. So.
Okay. I think that's a reasonable amount of time. Usually the student seminars I give are 3 to 3.5 hours long. But yeah, and I won't be offended if you decide to leave at any point at all. Feel free, of course. So yeah, I guess that's all the preliminary stuff I would say. I think, am I missing anything? Hopefully not. Yeah, so okay, string theory. What interested you guys in string theory in this talk? Anything? Yeah. Okay. I mean, I presume you're interested in particle physics. Okay, we're interested in particle physics. Fair enough. It's cool. It's cool. I guess you've seen a bit of particle physics, and you thought it was cool. Yeah. Nice, nice. Are you curious about it, about particle physics specifically? Yeah. Okay, very nice. Any other reasons why you came here? Okay, and I presume you like geometry and algebra. Okay, very, very fair. And again, these lectures aren't very math heavy, unfortunately, or fortunately, who knows? We'll see. So I definitely would have preferred more intense math, but I know not everyone would prefer that. So I'm sorry in advance if it doesn't satisfy your math hunger. Any other reasons? Okay, what do you know about string theory? What have you heard? You've probably heard a lot. I mean, most of you are in physics. You see stuff on the internet, people doing pop science. You've probably heard at least the name string theory, right? Have you heard anything beyond that?
Experiment and someone looked at it and said it looks like the equation for a string. That's apparently that's where it came about.
Yeah. Okay. Anything else? Yeah.
I know it makes predictions that satisfy both like classical quantum mechanics, quantum field theory, as well as actually gravity. So, valid.
Right. Anything else? Do you know what's the purpose of string theory? Why do people do string theory? What does it promise us? That's something fundamental theoretical physicists are interested in, ground unifying theory, unifying QFT with GR. Yeah, very good. But was that the initial reason why string theory was introduced? Oh, I'm going to talk about that here. So I forget the timelines, but at some point they were doing particle physics, I would assume around the 70s, and they were doing nuclear physics. So they were discussing these particles called hadrons. And feel free to ask me about particle physics, but I don't know much about particle physics. It's not in my field of expertise. I've never taken a course on it, so I might probably not be able to answer questions regarding particle physics. But yeah, and another thing, I'm following Suskind's lectures pretty closely, I would say. So yeah, anyways, they were doing particle physics. They were talking about these particles that come up in nuclear physics called hadrons. And hadrons and mesons, there are some particles that have some certain properties that's useful for particle physics. And they were looking at this graph. I don't think I need to use all the boards. I think we won't use the two ones at the edges. And if at any point, if anything is too small or too big, or if you can't read my handwriting, just tell me. I'm also really bad at spelling, so if I misspell anything, apologies in advance. They were looking at this graph, and this axis is the angular momentum, and this is mass squared, not mass, but mass squared. They were graphing these particles, like a spin half particle, like a proton, that has mass of, let's say, 1, right? We're scaling it such that this has mass of 1, and there are other particles with, and these go up by like half integer spins. There are other particles, and so what they found, actually, I should do this, that this made a linear graph. Okay. And they call this the Regge trajectory. Regge trajectory. In the fear of misspelling stuff, I'll purposefully not write stuff down and just say it. That way I can save myself the embarrassment of misspelling stuff. So yeah, they were looking at this, it looked peculiar to them, and they wanted to learn more about this. And if you're a particle physicist, this is interesting to you, apparently. So if you increase the mass of mass squared of these, you increase the spin because you're introducing energy to it. Right? A very important thing that will come up here is Einstein's famous equation, the mass energy equivalence relation, right? You've probably seen E equals mc squared. For most of the stuff, almost all of it, C and H bar are equal to 1. We work with natural units or Planck units. But we'll write this later on. Energy is the square root of p squared plus m squared, right? So there's more to it. There's also momentum. But in the simplified version, you've seen E equals m, and yeah. So mass has an equivalence to energy. That's the important thing. So yeah, if you increase the mass, you're introducing energy, so it changes the spin of these particles. And for different particles, they saw that there were these rigid trajectories that had the same slope, so they were parallel to each other, and that seemed interesting to them. So, as I said, these were they were studying hadrons in nuclear physics, and something about hadrons is that they can be spinned up. They're composite. They're not point-like particles. Really, point-like particles don't exist. Particles in general don't exist. We'll get into that a little bit. So maybe particle physics is a bit of a fantasy, but you can't really excite an electron. You can't really spin it because it doesn't make sense. Because we say it's like a point. Is it a point? Well, we'll say later on that it's not. But for now, it doesn't really make sense to spin something like an electron. It seems like a fundamental particle. And what is fundamental? We'll get into that question. That's a very philosophical one. But basically, it's not composite, as in you can't separate it into other fundamental particles, right? It's irreducible in a way. So yeah, they were studying these things in particle physics, and another interesting thing is meson scattering. Meson scattering, that you have these things that are Feynman diagrams. Have any of you guys seen a Feynman diagram? Yeah. Do you know how to interpret them? More or less. Okay. Yeah, the point of this is not to do particle physics, so this is kind of like a historical overview of how the string theory came to be, because initially it was not a theory, a grand unifying theory of fundamental theoretical physics. It was for studying hadrons and in nuclear physics. So you have these Feynman diagrams. And please don't ask me too much about this because I don't know too much about particle physics. Which you have pions. Remember, T is always going to be up for us, and space is always going to be that way. Right, standard relativity stuff. You have two pions coming in, and they interact through a row meson, whatever this particle is, and then they turn back into pions. And so apparently in quantum field theory that these should be dotted lines. In quantum field theory, there's another version of this. When you have a Feynman diagram like so, there's another one. If you have this one, you also have the other one that is just this, but rotated by 90 degrees. So how do you interpret this? Two pions separated, they come together, meet at a point, interact with according to this row meson, and then separate again as pions, right? Here, how do you interpret this? These are pions. This is a row meson, pion. Well, this is that, okay, you have a pion moving, right, in this direction. And then suddenly a row meson interacts with it and shoots the pion in the other direction. Same thing happens over there. And so these row mesons aren't unique. They have rigid trajectories, so it's like a family of row mesons. And if you add up all these Feynman diagrams, so you want to see the total contribution from these Feynman diagrams, you add up all the different row mesons. And people went to do this numerically. They found out that if you just do it for this one, it contains all the information you need. So you don't need the other one. And just summing up all the row mesons here gives you all the contributions you need and you have. so you don't need the other one. And this is absurd to people who study quantum field theory because they say, no, if you have this one, you also have to have that one, and you have to add both, like the contributions from both. It's absurd to pick one. You can't do that. You have to have both. But it seemed it wasn't like that, and they got interested in what was going on. So something peculiar is going on in this picture. So people such as Susskind were these other types of Feynman diagrams, like this, where Q minus is an anti-quark and Q is a quark. There were one of these, and they said if I were to look at this Feynman diagram like this, split it like that, it's analogous to, and well, okay, this symbol for me is analogy. It's analogous, right? To the Feynman diagram, the first one, this one. It's analogous to this, right? Two things come together, they interact, they move away. And they were doing this because they were thinking, oh, maybe it's not a point-like particle, so they don't meet at a point, but this like 2 points here, and there's a string in between them, and this is kind of how they interact, not by meeting each other, but there's like a string in between them, so the interaction doesn't happen at a point, but like they're smearing it out in a way, which kind of makes sense because things act on each other at a distance. They don't need to necessarily meet at one point to interact. So maybe this smearing out is a good thing. And these Feynman diagrams aren't really good representations of what actually happens. So yeah, they were drawing these. They said, okay, if I like cut it this way, it looks like the other one. And if I cut it that way, it looks like that one. So maybe this is like the fundamental Feynman diagram that I need to be studying, and not these two different ones. Maybe they're the same thing. I wrote down my analogy symbol, but I didn't say what it's analogous to. I just mentioned it. I didn't write it down. But this one and the other, the vertical line is this one. Okay, right. So yeah, so maybe things aren't point-like. Maybe it's smeared out, and maybe it's a string, and maybe that's how we can describe hadron physics. All of these were guesses. So now we're gonna kind of move away from the particle physics a bit and talk about some special relativity and energy stuff. I thought I saw a hand. Was there a hand? No? Okay. So you guys know about energy, right? So in this talk, a lot of the stuff will be hand wavy. So disclaimer, a lot of hand wavy stuff, both regarding the physics and the math. So you have energy, which is your Hamiltonian, right? Here we kind of say they're the same thing, right? For now, assume they're the same thing. And what does your Hamiltonian really look like?
E plus
What is T?
kinetic.
Give an expression for T. Very good. Very good. So it looks like something like this, right? Where if I write P squared, I mean P squared is defined as the L2 norm for the people who are interested in math of P as an element in a vector space. This isn't part of the lecture, just added in. Maybe you're wondering that. Okay. And so there's this plus this, and it's B because it's short for the binding energy. And this is the potential term we mentioned. And so let's look at special relativity and see what that thing is, what the B is. You guys have any guesses so far? So the Hamiltonian gives you a description of the total energy, right? How can you have energy? Well, your things can be moving, right? And that's described by the first term, p squared over 2m. Yeah. And p is the momentum, right? So it has information regarding the movement of the particles. And you said there's a potential term, right? How can you have potential? It's usually a function of position, yeah, but what causes? Generally, just like Hamiltonian mechanics. Yeah. It could be the quarks. You're probably talking about some potential that there is when there are quarks. Sure, that works. But we said that mass and energy are equivalent, right? There's an equivalence between them. So if there's no movement going on, there is still energy, right? And that's the rest mass energy, right? So if we go look at the co-moving frame of the center of mass co-moving frame, and what that just means is that go to a frame such that the center of mass is not moving. So if I have this piece of chalk and I spin it, right, around an axis, and I move it perpendicular to, like parallel to that axis of rotation, if I move along with that same speed in that axis, parallel to that axis, the center of mass of this isn't moving, right? So in that frame, the rest mass energy is mc squared. So now let's write down what the energy is from special relativity. It's summing over all the different particles, because your matter can have constituent particles, so you have to sum over all of them. The notation here is going to be very sloppy, so I'm not going to even write what this is, because in the lectures he didn't write what it is, but I'm summing up over all the particles, and p squared plus m squared. At the beginning, he keeps the c, so I'm also going to keep it as well. Why not? We'll eventually get rid of this. And this is technically supposed to be p I m I, and you're supposed to sum over the different i's, where your i's are just the different particles. First particle, second particle, and so on. So I'm going to factor out the mc squared from here, some basic math. Gonna factor out the m squared c to the power of 4 from here, take it outside of the square root. I'm gonna be very lazy with my notation. I'm gonna drop the sum. It's gonna end up being mc squared, square root of 1 plus p squared c squared over m squared c to the power 4. All right, just factored it out. Now I'm going to use a identity, which is just a Taylor expansion, or the binomial, or the Bernoulli approximation. Some of you might know it with that name. Is that this is approximately equal to 1 plus n epsilon, when epsilon is small. Using this identity, this is approximately mc squared 1 plus p squared c squared over 2m squared c to the power 4. I hope all of this is somewhat visible in the video. Let me check. Barely. Good enough. Okay. I should probably write bigger. Yes. This is equal to what? I should have kept it in one word. Doesn't matter. Is equal to mc squared plus p squared over 2m. Okay. Okay. This is familiar, right? So using Einstein's relativity, knowing this, right? We recovered this, and this looks very familiar in the Newtonian case or the Hamiltonian case. So you get this term, the p squared over 2m, which is the kinetic part, and you get the rest mass energy. So when it's not moving, it still has energy. The energy is not zero. It's this, and this is what they call the binding energy. Okay, interesting. Do you guys have any questions so far? Am I going too slow, too fast?
Is P the usual MV? Or is it an operator P?
Sorry, what did you say at the beginning?
Is P the usual like MV, or is it?
P. We'll define what P is. P is defined as when you have a Lagrangian. It's defined as when you take the partial with respect to the velocity coordinates, q dot. That's how P is defined. We'll define it later. But it could be MV. It is definitely MV in the Newtonian case. In quantum mechanics, it gets more interesting. Yeah. But it's the same P that you learn in Hamiltonian mechanics. Okay. Am I going too slow, too fast? Just right? Which one? Yes. Yes to which one?
No, you're good.
Okay. All right. So now let's imagine we're doing something. Okay. Let's boost whatever system we have in a certain direction. Let's pick the z direction. A lot. Let's boost it a lot in that direction. The Susskind gave it the name the infinite momentum frame because that's what you're doing. You're basically giving it infinite momentum in a certain direction. We're going to pick the z-axis to do that. And let's see what happens to our equations. Yeah, probably erase these and start here. Do you guys have any questions so far? You're probably wondering, how does any of this relate to string theory? So E is p squared plus m squared, right? Square rooted. Should probably write bigger for the camera. And so expanding this out, you guys know what it is. It's px squared plus py squared plus pz squared, right? Now I factor out a pz squared and move it outside of the square root. I'm just gonna give you what happens. It becomes pz 1 plus px squared plus py squared plus m squared over pz squared. And this approximately using Bernoulli's approximation is going to be this. Pz plus p squared. Okay, and I'll explain what p squared is. It's different from this p. I know it's bad notation, but Often we get lazy as physicists and just use bad notation because we're lazy, and it happens. So this p squared is just the px squared plus py squared. It's not the full momentum, the norm squared of the momentum. It's that, but because Susskind got lazy in the videos and I'm following that, this is where, yeah. So just remember this is px squared plus py squared. And we get this. So for the energy, we have to sum over all the particles. Sum over I, and this is the ith particle, ith particle, ith, ith. Very nice. Okay. So, and you know, is energy real?
Physically real or like
That's a good question. What do I mean by real? Let's say physically real for some definition of physically real. What if someone says the energy of this is something, and I say, no, it's that thing plus another thing. Yeah, that's a good way to put it. So the thing is, energy itself isn't really important for us. Can't really observe it. Differences in energy is what physically matters. It's what alters our equations of motion, not absolute energy itself. You can add a constant to your energy, your Hamiltonian or your Lagrangian, and equations of motion won't change at all. You've probably seen this in classical mechanics. So yeah, energies are equivalent up to constants, generalized constants. Whatever that means. That means that to get my equations of motion, I usually take something like a derivative, and whatever the derivative views as a constant, just ignore that. So it's like an equivalence class of energies, right? For a derivative, a number is a constant for this. What does that mean? More mathematically rigorously, it means it's in the kernel of this differential operator, right? Taking the derivative of a real number will give you zero, a constant real number. What for like the kernel? Well, any constant would satisfy this. It's in the kernel of this. What about any gradient of a function? That also satisfies this. You know that the kernel of the gradient is zero. So the gradient of a function is a constant of this. It means that when you act on it with this operator, you get zero. So we can get rid of this, right? Because it's just a constant. And energy is the Hamiltonian. Horrible Hamiltonian. Which is from quantum, you know, is I dt. There's an h bar there, but h bar is 1. Okay. So let's look at this. What does this look like? Well, compare this to that. Well, there's a px squared plus py squared, which is like the momentum squared, but like in 2 dimensions, x and y. There's a pz squared. It looks like the mass there. So this is kind of becomes your inertia. How's momentum inertia? Well, mathematically, it looks like that formula. And that formula, m is inertia, right? It opposes motion. Well, when we look at that, our pz is like our m. So is pz inertia? Does it oppose motion? It actually does. Right? The more the pz, the less the energy. Exactly like that. Kind of same here. But there's an interesting thing here. The energy is kind of proportional to m squared. That's peculiar. very interesting stuff going on. Very peculiar, I would say. But so you know that this is the Hamiltonian generates changes in time. You've seen this in quantum. So what if the energy is small? If the Hamiltonian is small, there's less changes in time, right? Your system will evolve less in time. The larger the PZ is, the smaller your energy is, the smaller change. So changes are also smaller. What is this? Well, why did I boost when I boost so much in a direction? When I'm moving so fast in a direction, things are happening slower. What is that? Yeah, say that loudly. Exactly. It's time dilation. And you're moving fast in some direction, changes are happening slower with respect to the not the lab time, but the initial reference time, frame time. Yeah. Okay. So when I move in the z direction, it's time diluting the dynamics in the x and y plane. And it's acting like inertia as we discussed. So yeah, PZ is like inertia, your mass, and m squared over 2 PZ is your binding energy. And the important thing about the binding energy is just that, like as one of your peers said, this is the kinetic is dependent on P, and this, the binding energy is dependent on position usually. This one, it's independent of the momentum. And the momentum here, again, is the px squared plus py squared. So it's independent of px and py, which is good. So this is looking very classical. We started with special relativity, but this form of the Hamiltonian is a very classical Hamiltonian, right? Well, special. Okay, something interesting. In modern days, special relativity and general relativity, Einsteinian relativity is considered classical. Quantum. So basically, what is classical? Classical is anything that's not quantum. Some agree with that definition. I personally kind of don't, because classical to me is anything before modern physics. So before like the ultraviolet catastrophe and like the beginning of the 20th century. But yeah, doesn't matter. So I'm Newtonian or like classical Hamiltonian. Let's stick with Newtonian, right? So started with this special relativistic description, got something that's Newtonian, from Einsteinian to Newtonian, when we boost a lot in a direction, a certain direction. And this is, well, non-relativistic. So in perpendicular to the direction you boost in, it behaves non-relativistic, as in Newtonian. So let's postulate something. Let's postulate that, I'll actually write this down. These are ideal rubber bands. I think this is important enough to write down that misspelling shouldn't matter that much, even if I end up misspelling something. Right? Let's postulate that. Why? Oh, anyone's guess as good as anyone else's, honestly. Why? Because of the same stuff we talked about. Let's imagine that they are. Why not? Right. So what is an ideal rubber band? A string. You have a bunch of particles. How many? We'll talk about that later. That create this, right? And it starts at 0 and ends at pi. And this is just a parameterization I picked. It can start at 0 and end at 1. It just has to be homotopy equivalent to this, whatever that means for the people interested in more math. And it's that. Yep. And we pick this specific parameterization because it ends up being convenient. We get rid of some pi's that end up in our theory. We don't care about pi's or constants or whatever. We want to talk about what it is fundamentally. So we pick this parameterization, and there's a continuum number of points here. It means that the cardinality of the set of points is continuum, right? So this is like, this is homeomorphic to the interval 0 to 1 on the real numbers. Okay, that's good. You guys look a bit bored. Are you bored? Do you want to get to the string theory? I mean, this is a string. We're saying what a string is, so I guess we're on the right path. We'll get there, don't worry. So, okay. What's the energy of a string? So this will end up being a bunch of points in infinite, uncountably infinite number of points, and they're springs between each two points. So you also have an uncountably infinite number of springs between each 2 points. So what's the energy of this system? Well, sum over all these, right? And so is this sum well defined? Well, we'll make it well defined using physicists hand wavy math. And okay, so we're assuming that all the masses are the same. That's the assumption that I didn't write down, but I'm telling you guys. All the masses are the same for each one of these. So no index needed here. It's a constant. And this is the velocity squared over 2 plus this, what is this? The string constant, sorry, spring constant, xi minus xi plus 1. You've probably seen this in classical mechanics again, over 2. So in the continuum limit, what happens? Well, we have uncountably infinite of them. But one thing we know about these strings is that when I take the continuum limit, so when it goes from discrete to continuum, I want the mass of the string to stay the same. So what does that entail for the mass of each one of the strings? It has to go to 0, right? It has to get small. What does that entail about the spring constant? Any guesses? If I take this to the continuum limit, what are your guesses for what's going to happen to k? Is it going to get big, small, stay the same? So it gets small?
Does it even like matter? Is it like the difference between xi and xi plus 1 getting go to 0?
Yeah. So it becomes like a derivative, foreshadowing here. But k does change. Imagine you have a rubber band and you're pulling like these 2 points on the rubber band. Okay. What if you pick 2 bits of the rubber band that are really close to each other? 2 particles in the rubber band that are really close to each other and pull on those. Is it harder or easier? Sorry? Yeah, harder. So when you take this continuum limit, k gets bigger and bigger. So in the continuum limit, it ends up your energy, your Hamiltonian, becomes your sum turns into what? An integral. What all physicists always do in the continuum limit, they turn the sums into integrals. And somehow magically works out, and it takes like 8,000 pure mathematicians to prove that it's actually very valid. Yes. because it was a typo. Thank you. So you write down speed squared, and this is a function of sigma, right? It's our parameterization over 2 plus half, and what is this? It's the difference. Okay, well, when we make it infinitesimal, what happens? It becomes the derivative. Again, very hand-wavy math, but it ends up working out, you know, which usually does in physics, and this is also a function of the parameterization that I'm too lazy to write down. So each one of these boards are like, there are kind of borders that are hard to see, but that's what distinguishes the board. So this is not being multiplied by 8, right? Okay. This is the kinetic term, this is the stretching potential term, and this is what you have for your Hamiltonian. For your Lagrangian, what happens to this expression? Energy plus potential, what happens in the Lagrangian case? Yeah, this plus becomes a minus. Very good. I'm not gonna bother writing it down. I'm just gonna check how much battery I have on this laptop. But yeah. So okay. This. The energy is proportional to mass squared. Very, very peculiar. Let's write this down. Okay. And this is the internal energy of the mass of all the constituent particles. Okay, strings are like springs, which are harmonic oscillators. And, well, you know from quantum mechanics that harmonic oscillators are quantized. You've studied that in your quantum courses. So, strings again are like infinite number of particles, and between each one is a harmonic oscillator. There's a spring, and the whole thing, the whole string is a rubber band, and it acts like a spring, a composite spring that has masses, a massive composite spring. Okay, so yeah, and these there are these uncountably infinite harmonic oscillators that we need to quantize. Okay. Any questions so far? Am I going too fast, too slow? I take that as I'm going too slow. Are you understanding everything? Alright. Okay. So let's take this string, stretch it out to length L. And let's look at that term. Di x y sigma. Oh, and this is notation. This is standard notation for you taking the derivative. You're taking the derivative, the partial derivative of x with respect to sigma. Usually you write it as a fraction, but lazy notation actually ends up being a good thing. You know how the saying goes. In order to be a good mathematician, you need to be lazy. So that's what I'm striving to be, as lazy as possible, without being wrong. And that's, I guess, the important part. So this is proportional to length over how much we parameterize it over, which is pi minus 0, which is pi. And I don't care about the pi. We don't care about constants. I'm going to get rid of that. Right. So what does this entail? This means therefore. Therefore, this, which is the expression I have there, is proportional to length squared. This is length, not spin. And which is, I should have written it there. I'm so stupid. Which is m squared. Why? Because this part is this part, the kinetic term, and this part is the potential term here. So it's proportional to that. Okay, nice. So what does it mean? L is M, proportional. And this is the length, and that's the mass. So then Susskind talks about quarks and anti-quarks. I don't know much about them, but it's a brief tangent, I guess. So I thought I might tell you guys as well. This is a quark, this is an anti-quark, and they make a flux tube between them. So there are these magnetic field lines that are going through them, and the energy density is uniform in this whole thing. And this is a energy density, energy over length, over unit length. So the total energy you get is going to be proportional to L. Because you have to multiply it by the length to get the total energy. And it turns out to be useful in field theories. And so I talked about if I have the string made out of particles, which is funny because I said particles are made out of strings, but now I'm saying strings are made out of particles. So begs the question, what are particles? Great question. So if I stretch the string, make it longer, I want when you have an actual string, you pull on it, you make it longer. You're not creating new particles. It's just the distance between those particles is getting more. But here, what happens is that when I have this continuum, you actually end up creating new particles when you stretch it, right? And that doesn't happen with a rubber band or a balloon or whatever, right? There are these atoms, right? Some finite number of atoms, a lot of them are still finite, and the distance between them is getting more. But when the density, well, when I stretch them to stay the same, like the mass density, that doesn't happen when you have a rubber band or a balloon or whatever. The density gets reduced. But here I want it to stay constant. So new particles get created. And this is, well, kind of suggestive in a way that when you have quarks and you, well, pull on them, the energy you spend on pulling these quarks apart ends up making new pairs of quarks. You've probably seen or heard of that in particle physics or some nuclear physics, right? So the energy you put into pulling them apart turns into new quarks. And that's is kind of what's happening here. Interesting. Any questions?
One way then it is like this notion of strings connected to color confinement, because that's like partly why putting energy into separate quarks is quarks, right? Because quarks are color confinement. So I don't know if that's even part of the lecture.
So Susskind doesn't talk about that yet in the first 4.5 lectures that I watched. He doesn't talk about that. Maybe he talks about it later. The answer is I don't know. I don't know. But we'll talk about kind of, yes, I don't want to spoil anything, but we'll talk about how these strings manifest as different particles. Okay, so let's go back to our whatever we were saying about energy. So E is E squared plus M squared, right? When M over P is huge, right? So the ratio of mass over momentum is huge. What do you get? You get E is M plus P squared over 2M. this is the non-relativistic limit, right? When things are moving very slow, the ratio of mass over p is large, right? Because momentum is so slow, you get the non-relativistic energy, the same thing Newton said. Now, what about the other case? Whenever m over p is really small, what do you get? You get the thing we got there. The peculiar energy we got there, which is p squared. Remember, it's the projection of p on the perpendicular subspace of the direction in which you're boosting. So here would be the xy plane in 3 dimensions. Is 2 over 2pz plus m squared over 2pz. You get this in the relativistic limit when you boost a lot. Okay. In here, energy is proportional to mass squared. But here, energy is proportional to mass. Oh, interesting. Something to know. So it seems that when you boost a lot in one direction, you need one less dimension to describe how these strings interact, how these strings, like the dynamics of these strings. And this is actually related to the holographic principle, which you might have heard. It's a way of thinking of the grand unifying theory of fundamental theoretical physics. You want to have a quantum gravity theory in the bulk, and you can allegedly, well, this is what they're trying to do, describe it as a quantum field theory on the boundary of that. And so the boundary has one less dimension, as you know. If you have a manifold, the boundary of the manifold has one less dimension. So let's study these strings, not to do hadron physics like they were initially came to be, but maybe as something more, maybe as a theory of quantum gravity, maybe. We don't know. But maybe it's useful for that. Again, a lot of maybes. So, okay, if you have the energy of a rotating system, what's the energy of a rotating system? It's this is a small tangent. Yeah, Susskind goes off on a lot of tangents, so bear with me. The energy of a rotating system is L squared over 2 moments of inertia. And this is in quantum mechanics you study, this is n h bar squared, this is 1 n squared, sorry, over 2I related to Bohr's quantization of the angular momentum of the atom. And to introduce energy to increase the angular momentum by 1 quanta. Because we're saying these are quanta, as in they're discrete. The energy spectrum, the angular momentum of the spectrum for these are discrete. So, yeah. So particles that have a lower moment of inertia, such as an electron, right? It's very small. What happens here? Well, this will get really huge. Right? So if you change the angular momentum by 1 quanta, because it's divided by a very small number, the energy will jump by a lot. And you see this huge gap in the energy. Right? What happens when I is big? Well, if I is big, you're dividing by a big number. Let's say if you have a basketball versus what we discussed, which was an electron. If you change the spin by 1 quanta, if you increase it, you divide it by a huge number. you don't get much of a difference in the energy, right? There's not a huge jump in the energy. Okay. You've probably seen in quantum mechanics when you draw the energy spectrum, it's like, oh, there's one here for like the electron, this and next one is here, the next one is here, the next one, or whatever it looks. And maybe it gets like the distance increases as the energy goes up. I don't remember, it doesn't matter.
And levels decrease.
Okay, then good, it's what I drew. But doesn't matter. You see these gaps as you increase the angular momentum by a quanta, and when you look at the energy spectrum, you can see the gaps. But what about the basketball? Well, the math, it tells us that the gap isn't that much. If you increase the angular momentum by a quanta, you won't get a huge jump in the energy spectrum. Okay. That's interesting. So there's a difference between kind of a basketball and an electron. But we're saying everything is made out of particles. So what's going on here? That begs the question, what are particles? Yeah, for a basketball, it would be so little that basically in the energy spectrum for a basketball, you'll see this. This is what you'll see in the energy spectrum. It's basically a continuum. Keyword basically. It's not exactly a continuum. It's still technically discrete because the world, well, we think is quantum. So if it's quantum, that can be a continuum. It has to be discrete. But when we look at it, it looks pretty continuum. So yeah, this will tell you how much things act like particles versus how they act classically. That was the first lecture. Now we move on to lecture 2. Any questions? Wonder if my laptop will survive for this in terms of its battery. 40%. I'll probably I hope there's an outlet here. Ah, there's one here. Okay, sure. Feel free to ask questions or take snacks or anything you want. Exactly. Well, the question was for the microphone because probably can't hear you. It's because the distance between the different energies in the spectrum is so small that it's basically continuum. Yes, that's how we're treating it. It looks continuum for basketball because the what is I? I forget what I is. The name of I. Moment of inertia. Thank you. Is so large that it, the difference in energy is very small. So it's basically continuum. Should have done this when my hands weren't chalky. Okay. It's charging. Very nice. Okay.
Question.
Yes.
How similar is the order of materials that lecture to the order in which the theory was developed? I mean, I know a lot of this is just like prerequisite math, but we have to find like relativity stuff we already know, but like string theory was.
That's a good question. So the question was, how does the order of the stuff in the lectures relate to what historically was discovered? chronologically. I'm not sure. I would guess pretty accurate because Susskind was one of the pioneers of string theory, and this is kind of starting from the beginning. So I would say more or less very similar in their ordering. Yeah. Any other questions before we start lecture 2? Okay. So lecture 2 is just a bunch of well, the first part is a bunch of preliminary math. Motivations. I guess reasons, you can't really say what are the reasons for a postulate, except that it's experimentally verified. So in math, you have axioms, and axioms are things that you take to be true without proof. Whereas in physics, you have postulates. And people use them interchangeably, but they're not the same thing. In physics, you have to experimentally verify. And by verify, I mean it has to be falsifiable, and you have to not disprove it using experiments. You can't really prove anything in physics. You can just say, oh, I didn't disprove it. Exactly.
Experimented, and that's a reasonable postulate.
You can definitely have motive, like motivation to why you postulated something, but usually it's like an educated guess. Okay. Preliminary math. So you have a discrete function, you want to approximate it as a continuous function. This is xi, the positions, it's from 0 to pi. For open strings, our parameterization is from 0 to pi. For closed, it's 0 to 2 pi. Again, just convenience. It's just the convention. I is an index set from 1 to n. Delta x is what is xi minus 1. And well, this is the same thing as the partial derivative with respect to psi times delta psi. Converse yourself of that. I'm going to breeze through this part of the lecture. X is class infinity functions, an element of the class infinity functions of psi, of sigma. So it's smooth. Delta sigma is pi over n. Yeah, it is a very nice function. And this object that I have here in the continuum limit, right? I'm not going to write down continuum limit because I'm lazy, but I'm going to tell you that this is the continuum limit, becomes the integral from 0 to pi of x parameterized by sigma d sigma. Now we're going to talk about boundary conditions, the same ones you've studied in PDEs. You have a Dirichlet boundary condition, DBC, boundary condition Dirichlet. What is it? It's that, does anyone know? It's this. The two endpoints are fixed at the 0. More specifically, they're fixed at the same point. So what does this look like? This is your string. Right. Normal boundary conditions. Boundary conditions, you've studied all of this in PDEs, so I'm not going to spend much time on this. It just says that the derivative at the two endpoints is 0. So it'll look something like this. Really analyze my function depending on what boundary condition it has. So for Dirichlet, it's sigma sum over n, and n goes from 1 to infinity, but I'm gonna not write this anymore because again, lazy. Xn sine n sigma. This is for Dirichlet. For Neumann, it'll be equal to sum over n, xn cosine n sigma. Again, you've studied all of this in PDEs. This is where you have Fourier analyze them. Very boring stuff. Important identity. Cosine n sigma, cosine m sigma is d sigma is equal to well 0 if n is not equal to m, pi over 2 if n is equal to m not equal to 0, and pi is m equal to n equal to 0. I know, pretty boring stuff. Sorry. Okay, now let's talk about physics. That was math, end of math. Now let's bring in the physics. Let's talk about the energy of the harmonic oscillator. Harmonic oscillator energy. Probably shouldn't put it in the energy of the harmonic oscillator. Yes.
If you have x, the subscript of x start at 0, because for delta x is equal to xi minus xi, x of I minus 1, you at I equals 0. No, at I equals 1, you would have x1 minus x0.
Yeah, you didn't include n equals 0 in your
Yeah.
summation.
For I zero.
This one, you mean?
No, the delta x equals. On the first one.
Oh, yes.
So then at I equals, so you can have x sub 0.
Well, you can have x sub 0, it's just I can't be 0. I can be this, right? Because if it's 0, then what's x of negative 1? Doesn't make sense. Okay. Energy of the harmonic oscillator. E equals x squared over 2. It's mx x dot squared, but I'm rescaling my x dot to eat my m. You can always do that, right? I'm just rescaling your x so that your x dot squared gets rescaled such that the m is inside of it. Because we don't care about that. Doesn't matter. You get this. Now, you've studied this before in classical mechanics. You know that this is squared over 2, x squared. So, and for the Lagrangian, again, you change the plus to minus, easy. For a quantum harmonic oscillator, the energy is quantized with omega. Fair enough. So K is, yeah. So what is omega? Omega is the square root of K. Okay. Now, what's a particle? Let's talk about this a little bit. We say strings are particles with springs in between them, but that's kind of very circular. So what are the properties of particles? Any guesses? What do you want your particle to have? Be very general. Something like very obvious. You said charge, sure. Mass, good. Anything else? Velocity, very good. Spin, anything else?
Are you missing a two at the epsilon?
Flavor and color.
Where?
The epsilon. Yeah,
Two.
so a superscript.
Oh, yes. Color, sure. You said momentum, but also position. Probably the first obvious one, position. Right. Well, that coffee mug there, that satisfies all the things you guys said. Is that a particle?
Irreducible.
What does irreducible mean?
Those you have two things that make up a particle, that one of them has to be the identity.
One of them has to be what?
One,
One?
like
So like one element, and as a set, as one element. Well, an electron, we say is a particle, but it's not a point. It doesn't have one element, it doesn't occupy just one position in space.
Are you talking about anything? I think of the subatomic thing,
Mm.
particle.
Define subatomic. So about 10 angstroms, or no? I think so. I don't know. Okay.
Force carrier?
Force carrier. Interesting. Interesting.
Which itself needs to be defined. Anyway, like, whatever.
Right. Good guesses, really good guesses. But you would say like the first obvious one's position, momentum, mass. But this coffee mug, it's not a particle in like the sense that we call things particles. It's usually about their energy spectrum, interestingly enough. So we have a ground state, and the ground state is in the vacuum. The vacuum is basically when there is nothing in space, completely empty. The ground state, you have stuff, like you have a string, but it's not vibrating. All the modes is in the zeroth mode of the different particles. It's not vibrating. That's the ground state that we'll talk a lot about. So then you have excitations of this. Imagine you have a string, you poke one of the particles in that string, it starts vibrating, you excited the energy of the ground state, now it goes to a different state, an excited state. And if I draw like the excited states of a particle such as an electron, this is the energy spectrum of an electron. It's like this. Okay. But what about for like a basketball or a coffee mug? Well, I can excite this such that you don't really see the gaps. Again, we talked about this in the last lecture. It's kind of a recap. And that's practically continuum. It's not continuum because everything is quantum, so that is quantized, as in they're discrete, but so close together is practically indistinguishable for stuff that we touch and see in regular stuff that it's so small it's practically a continuum. And that's kind of what distinguishes particles from things that aren't particles. Okay. Now enough about particles. So if I want to describe something using non-relativistic mechanics, what should my system satisfy so I can describe it using Newtonian mechanics and I don't have to use special relativity? Very good, very slow compared to the speed of light. Um, but okay, let's say I'm spinning this around some axis, and the ends of this chalk are spinning very close to the speed of light. But yeah, the center of mass of this is not moving at all in our frame. Can I describe this using non-relativistic dynamics? Maybe. Well, the thing is, every single particle that this is made out of has to be going slow. It's not enough that the center of mass is going slow, or most of the things are going slow. If I have a box full of particles and they're going at very high speeds inside of the box, but the box isn't moving, I can't describe that just using Newtonian mechanics. Even if there exists one particle such that it goes at very high speeds and I can't really approximate it using Newtonian mechanics, it fails my approximation. So all of it has to be moving at very low speeds for that to happen. Okay. So how can we get that? How can we get things make it such that things are moving slow compared to the speed of light? So we can use Newton's description, which is easier than doing relativistic dynamics. Well, at the beginning, we talked about if we boost our system in some direction a lot compared to the speed of light, we saw that time dilation happens in the perpendicular directions to the direction of the boost. And we saw that the Hamiltonian takes the form of classical Newtonian mechanics. So that's actually the trick. Whatever system you have, boosted a lot. When I say a lot, I mean compared to the speed of light in some direction. Let's pick the z direction. Doesn't matter. And then the dynamics in the perpendicular directions becomes Newtonian. And we saw that at the beginning. And I think that's really cool, if you ask me. And then we take ourselves to the co-moving frame of the center of mass. So we move along the center of mass, and we just look at the projection onto the perpendicular directions to the direction of boost, and that has a Newtonian description. We drop the dimensions by one, as we discussed. And that's really interesting. And it turns out that kind of magically, strings have this property that the dynamics in those directions is determined by the other direction. But we'll talk about them later. So going back to our trusty strings, we have an open string, right? 0, pi. What's the energy of this? Is you sum over all of these, and each point, each particle. I'm using particles very interchangeably. I'm sorry. Each constitutive matter that this string is made out of. No. I'm going to sum over all of the particles, all the bits of the string, and get the total energy for this string. The parameterization?
Yeah.
It's 0 to pi? Oh, convention. Yeah, because it turns out that it'll cancel out some numbers and it'll look nicer. Oh, the shape? Arbitrary, just threw it. That's what my hand did. Right. So each one of them has mass mu constant. We're assuming that they're all the same. X dot I, x dot squared over 2 plus k. You've seen this, I'm gonna go fast. We want the analog mass to be fixed. So the mass of the whole thing, the analog mass to be fixed. So mu has to be equal to 1 over n. When we increase the number of particles, we want this to the whole thing to stay constant. There are n number of particles. If each one has mass 1 over n, we fix the total mass to be 1. Perfect. That's what we want. And that's what we already talked about. We want the mass of the whole string to be fixed. So this is, I said, the string is basically composite spring. Right? Like that. Bunch of particles, springs between them. So for composite spring, you've probably studied this in classical mechanics. Composite springs are easier to stretch for a given k. As in, you have k and k, you compose them together, and this whole thing has a spring constant of less than k. So in order to fix the k, your k has to go with n, like be equal to n, proportional to n. The pi square is just to get rid of the pi's because we don't want to have pi's. And this just comes from studying composite springs. Sorry. Yeah. And so delta sigma is the length of that parameterization over the number of stuff you have. And very good, very boring stuff so far. Okay, now we want to, what time is it? Okay. So the kinetic term, I'm going to erase this. Actually, okay, so let me see if I can skip stuff. The kinetic part of the energy is what? This, right? Plugging in all of the stuff I have here, just manipulating it, I get 1 over n xi. So I don't think this part is important, so I'm gonna go very fast. And in the continuum limit, you get an integral, which is going to be 1 over 2 pi integral from 0 to pi squared d sigma. Taking the derivative with respect to tau, tau is in the co-moving frame. We're moving with the system. Good. Now, what's the total energy? This is, okay, look at this. And this is this. Sorry. This is delta xi squared over 2. And the continuum limit, delta becomes a derivative. Very good. This is the energy of a wave field. If you, in a field theory, study waves, this is the energy for it. Interesting. Interesting. So the energy of a string gave us the energy of the wave. Wow. Interesting. You have a string, 2 endpoints fixed. There's a wave moving this way. What will happen? it'll get reflected and move that way. But it will get reflected with respect to the y-axis and x-axis. So if it's moving to the right, it'll hit this directionally boundary condition, then move to the left, and it'll also be reflected across the x-axis. So it does that. If it's Neumann, what happens? You don't get the flipping over the x-axis, only the y-axis. So if it's going to the right, it'll just go now to the left, but it won't flip like that. So, okay. Let's study, okay. You have points. This is the nth point. There's a spring to the n-1 point. There's a force between these F, and this force is going to be equal to K delta X, Hooke's law, and so this is going to be N, because K is proportional to N, as we discussed, delta X, and this is N derivative with respect to sigma X, and delta X, delta sigma. And that whole thing is going to be, this is equal to pi over n. And when you simplify all of this, you get this. Okay. So math, that doesn't matter. I want to talk about the theory. So yeah, that's your force. Okay. Which is equal to Newton's second law, because now we boosted so much in a direction that in the perpendicular direction, it's now Newtonian. So we can use Newton's second law. It actually works here. So in the grand unifying theory of physics, when you need special relativity and general relativity, so general relativity because SR is a subset of GR, and quantum, we're actually describing your strings in the Newtonian case. This is a Newtonian description of strings. We're using a Newtonian description of strings to unify quantum and gravity. Isn't that hilarious? I think it's a bit hilarious. Which all goes back to when you boost something so much in a direction that in the perpendicular direction, it's Newtonian. I find that kind of crazy. Very remarkable, very remarkable. That's just my opinion. This is 1 over n x. I should have used the chalk holder that I have. I didn't bring it. Doesn't matter. I knew I forgot something. That's what I forgot. Okay. Wait, we have this. So rearrange this. What do you get? The acceleration is n. Okay. We want to take the continuum limit as the number of particles goes to infinity. As n goes to infinity, what happens to the acceleration? Yeah, it blows up. You get infinities. Ooh, that's not good. How do we fix that? I want this to not blow up. Well, this has to account for that. Okay, so if this is 0, then I won't get an infinity. That's good. What's this when it's 0? It's the Neumann boundary conditions. So in the study of string theory, the Neumann boundary conditions are the one that's useful. And that's the one we'll focus on. Okay. What's the Lagrangian? This is the Hamiltonian, which is the energy, same thing. The Lagrangian is when this is negative. Very easy. Any questions? Good. Should I erase? Where should I erase? I'm just going to continue here. Let's Fourier analyze the Neumann boundary condition for X sigma. We already discussed you get n 0 to infinity, xn cos n sigma. what is x dot sigma? It's technically sigma and tau, and you get and 0 to infinity of x, and the time dependence is the Fourier coefficients. And the spatial component dependence is in the cosines and your bases, Fourier basis. So I'm gonna skip some math. What can I do here? Can I skip that? I want to. Well, it's 1 over 2 pi integral over d tau x squared d sigma, what we have in the Hamiltonian or the Lagrangian. You can work through this, but you get sum over n equals 0, m equals 0, infinity of x and x m. Pretty easy stuff, I hope. Should be trivial. Cosine n sigma cos m sigma. You know, I don't want to skip the math, but also want to get to the physics. You know, it's hard. So bear with me. We studied what this integral is previously. When you plug in the identities that I told you for the preliminary math, you get this. The physics is the important part, you know. The math isn't. Well, the math is too. I love math, but you know, you gotta do stuff. Can't spend all your time manipulating the math. So that's why we picked this parameterization that you asked about. So it cancels out. And the same thing for a di sigma x. This is actually, I'll skip that. I don't just write down the Lagrangian. Write it here. So you're just using the identities and like plugging in the Fourier analyzed into the function. And the Lagrangian becomes x2 over 4 n xn squared minus 4 n squared xn. Oh, okay. What is this? X naught dot squared. That's the velocity of the center of mass. So from the Fourier analysis that you've seen in PDEs, you get that term, and that has a physical meaning to it. It's the center of mass, the velocity of that squared over 2. That's the kinetic energy of the center of mass. Very nice. And the rest is everything else is the internal energy. This is the kinetic part of that, and this is the, what do you call the potential part? So looking at that, but with the minus sign, because we're talking about the Lagrangian, omega squared, n squared, omega squared is n squared, omega is n. Yeah, exactly, but okay, I don't care. Yeah, I don't care about numbers. I care about the physics. Okay. Simple harmonic oscillator. Let's quantize it. Any questions? Questions? Okay. I used like half of the chalk, which is crazy. Simple harmonic oscillator has energy. The energy spectrum is h bar n omega. We're using n for other stuff, so I'll just call it q. It's some integer, right? But h bar is 1, so this is q, which is some integer, and omega, right? Frequency. We're using q for another. Sorry, not integer, natural number, which is equal to qn because of that. Frequency is n. Okay. So in the x and y plane, we've studied the raising and the ring operators in quantum, right? A is for the x direction, and for the y, I'll use b, right? A dagger is a raising operator, and A is the lowering operator, as you know. If I have the ground state, so that's usually denoted with het 0. How do I get the first excited state? How many ways are there of getting that? Well, how many ways are there of getting that? If I have a raising operator. Exactly. How many raising operators do I have? One for the x direction, one for the y direction. I have 2. There are 2 ways of getting the first excited state from the ground state. This is only, you have one of these. In 2 different ways, you can get the first excited states, as we just discussed, either using A dagger or B dagger. A1 dagger, B1 dagger. How do you get, how many ways are there of getting the second excited state? Any guesses? 4? That's a good guess. Any other guesses? One way is to apply the raising operator, the x raising operator twice. A1 dagger to the power of 2. Okay. Well, I can do the same for the y direction. Now I can do one y and one x direction. I can also just apply the second x direction raising operator once, or the b. So same thing for the b. 1, 2, 3, 4, 5. 5 ways. No. No.
I feel like, yeah, I feel like it's some sort of like constant disenfranchisement.
That's a great question. Let me get back to you on that. But it's related to the different harmonics of these frequencies. So each one of these frequencies, we call it as a harmonic. And it's related to that. But let me think about it and get back to you. Okay? Does that sound good? Okay. Okay, so 5 ways. And usually in quantum mechanics, you study for if you have the spin is J of a particle. Well, J is sorry. The jth excited state. What am I saying? The jth excited state has 2 J plus 1 ways of getting. Yeah, exactly. Yeah. So, okay. If we have open strings, imagine this is a quark and an anti-quark. Quark, anti-quark. I'll denote the anti-quark with an open dot. it can interact with another quark and anti-quark and give you just one string. Okay. And that's the end of lecture 2. Lecture 3. Any questions so far?
So strings you can say are actually between two quarks.
It doesn't have to be quarks. In that specific example, it's quarks. So in that example, it's quarks. Doesn't have to be quarks. Any particle, we're going to say every particle is just going to be strings. Different strings vibrating in different harmonics. And those create different particles. Yep.
Just, okay, clarify for the energy over here.
Yeah.
What does power do?
The time in the co-moving frame. So we're moving along the center of mass of our system, and it's the sorry, it's the proper time. It's what the time of the system, what it experiences. So your own time, not the time I measure for you. It's the time you measure on your watch. Sigma is the parameterization of our space. So a string, whether it's open or closed, it's a one-dimensional manifold, right? There's only one dimension to it. And you've probably heard string theory happens in higher dimensions, but a string is a one-dimensional object. That's very important. That's crucial. So pay attention to this. It's a one-dimensional object and one-dimensional manifold. But we do some embeddings in higher dimensions. But the strings themselves are one dimension. Whether it's closed or open, it's a one-dimensional manifold, as you would suspect a string to be. And we parameterize it using sigma. So sigma just says which point are we looking at, and this does not have to be embedded in Rn. We will end up embedding it in Rn, and the sigma basically tells you what position in the Rn it will take. But abstractly as a manifold itself, you can parameterize manifolds. And that's what sigma is. Okay. It's 8 p.m. right now. So I have a bunch of stuff. I want to see if I can speed run this so I can get to the interesting stuff faster. I probably should have not spent a lot of time at the beginning, but I want to talk about how strings interact. Definitely. So yeah, I'll try to go as fast as I can, skip the boring parts, because I don't want to keep you all, here all night, obviously. Unless if you want to stay here, then I'm open to staying here. I don't have anything to do tomorrow except file my taxes. So, okay, lecture 3. Any questions? Okay, energy of string. Okay, now it's going to be written in the Fourier coefficients because we Fourier analyzed it. Over 4, we talked about the energy on the right board is over there, and squared over xn. And so this is the position, chi is the position, and x is the Fourier coefficients. Just how I write it. Kinetic potential, we're lazy, so we're dropping the sigmas. The Lagrangian is going to be this with a minus sign. I'm not going to bother writing it down. N is the harmonics, also known as the frequencies. P, someone asked, I don't know if they're still here. Momentum is defined as the derivative of the Lagrangian with respect to the velocities. You've seen this in classical mechanics. In this case, it's just going to be x dot over 2. Right, I just rescaled my x to have the mass inside of it. Very just clever trick because we're lazy and we don't want extra stuff to write down, so we don't care about them. We want to get rid of them. And so this says that my Hamiltonian, which is my energy, is going to be En squared plus n squared over 4 x squared. This is the Hamiltonian description instead of the Lagrangian description, right? The reason why I didn't write Hamiltonian because Hamiltonians you usually want to the coordinates in which you describe them are momentum instead of velocities. Velocity is a Lagrangian description, and this is how you get the momentum. The Hamiltonian is just the Legendre transform of the Lagrangian classical mechanics stuff. Now, okay, we have this. Okay, wait. Now we're going to do something. This is for a harmonic oscillator. How do you quantize it? Okay, you probably in your quantum mechanics classes you use something like okay, a squared plus b squared. This is equal to a plus ib times a minus ib. The I is the imaginary number, right? Use this. You decompose that. Okay. You get your Hamiltonian is equal to n nx over 2 plus ip nx over 2 minus ip, and you want to define your raising and lowering operators, a and a dagger. The thing you want to satisfy is that the Lie bracket of a lowering and a raising is 1, and each exercise check that this satisfies that it does, and that the important thing that x and p, the Lie bracket is 1. So the commutator is, I guess, what you know it as. This is a. Okay. From this, you deduce that the raising and lowering operators is going to be just you go through some math, doesn't matter, minus plus I over square root n, n. These are your raising and lowering operators. From this, you have 2 equations, 2 unknowns. You find what your x is. Xn is going to be raising operator plus a over square root n. You do the same for y. We kind of neglected y. There's a y direction. We kind of forgot about it because we're too lazy to write it down. Doesn't matter. But written in terms of your raising and lowering operators is this. What about the units? Oh, this is length. These are raising and lowering operators. How does that work? So this is something peculiar going on with the units that we'll talk about in later lectures, if we get to it, or if not in part 2. So yeah, the x, that's the Fourier coefficient, but x sigma tau is sum over n over square root n cosine n sigma. Fourier analyzed it. Very good. Okay. End of that. Now let's talk about the spin of massive and massless particle. Any questions so far? Next theorem in lecture 4 that I want to tell you guys about because I think it's very magical, very neat. So that's why I want to quickly get to that. So the spin of massive and massless particles, as we said, spin J has 2J plus 1 states, 2J plus 1 total states that we talked about over there. For massive, this is for massive particles. So yeah, in some direction when we have this particle and it's spinning like this, the right-hand spin says, oh, it's plus 1, left hand is -1. If you move at the co-moving frame and boost in the perpendicular direction in direction 0, what does that mean? It means that if you move with this particle and then you do a boost in the other direction, it seems that the angular momentum is perpendicular to this direction here, so it has spin 0. So it's not going that way, no that way, it's going perpendicular, so it's 0. Yeah, please still this. Very nice. For massless particles, any Lorentz transformation leaves it moving at the speed of light. You can't. You only have two states. One is a maximum and one is a minimum, and they're negative to each other, and you don't get a 0. You get nothing in between. So for like the second excited state, the spin 2, well, angular momentum 2 that we talked about, that has 5 different configurations, so 5 ways that you can get there. Sorry, so what am I going to say? For this has I forget the name of them. The angular momentum is -2, -1, 0, 1, and 2. This is for a massive particle. It's related to how many different configurations of raising operators we use to get there. Another way of thinking about it is that you have 2 spin 1 particles moving this way. Other ways is that one is spinning that way, one is spinning that way. They cancel out. You get 0. Both are spinning that way. You get -2. You can't end up getting 1 or -1. So for yeah, exactly. Well, I guess I spoiled what I was trying to get at, but you've maybe seen light polarization in optics. This is, for instance, the y direction, the x direction, and you have these states, right, polarized in these 2 directions. This is linear polarization. I define the perpendicular polarization to be sorry, the circular polarization to be one is R, which is defined as this, and one is you call it L. This is right-handed polarization, circular polarization. This is left-handed. You can kind of see how that is. Okay. So for this, if you have like a photon, so that's spin 1. Angular momentum is either parallel or anti-parallel to the direction of motion, as we said. For massless particles, Lorentz transformations will leave it moving at the speed c. Can't change it because it's always going to be at the speed of light. For massless particles, Lorentz transformation can't change that. So that's why you get these, and you can't get the 0 spin that we talked about. Gravitons are massless spin 2 particles. You've probably heard this in particle physics. And it's like having 2 photons because photons are spin 1. So if you have 2 of them, they can either both go spinning right or both spinning left. So you get +2 or -2. We just talked about for massless particles, the total angular momentum you have is either one maximum or one minimum. You have nothing in between. So it's always 2. For these, we said, oh, okay, it's like 2, 5, and for 3, what's it going to be for 3? 2 times 3 plus 1, that's 7. But this is for massive particles. For mass, this is only going to be the maximum and minimum. For 3, it's going to be what? 7 and -7 for the angular momentum. Okay. So the yellow line, also known as the first few lines on the spectrum of states, is uh, give me a second. We already talked about that. You know what? I'm gonna skip this. Also talked about this, the ground state. There's some overlap because like he likes to review stuff and from previous lectures, which makes sense, but because this is all contained in one, I don't want to review stuff, it's redundant. We might guess for the harmonic oscillator, the ground state is half h bar omega, which you've probably seen like in static or quantum, but let's not impose our prejudice here and see what it actually is. Okay, every harmonic oscillator has well oscillations because of the uncertainty principle. So even if you think it's not oscillating because there's of the uncertainty principle, you can never have like no movement at all. Okay, let's excite by one quantum of energy. What will that look like? I think we're going at a pretty good pace. We can give a very nice theorem very soon. And then you guys can go home and enjoy your Friday night. Well, if anyone asks you what you did on a Friday night, you can tell them I learned string theory, which is probably not a common answer people would give to that question, I imagine. I could be wrong though. So let's excited by one quantum of energy. We have our ground state. We're exciting it for with the in the x direction. There's also the y direction with the b's, but let's ignore them for the sake of time. It's the same. You get this. Yeah, you know, we said, well, it's just proportional to the mass squared. And now we're adding one unit. What does that mean? The units seem to be very off, but units we talk about later. I don't think we'll get to in this lecture, but like yeah, in this talk. But take it as what it is. We're exciting it by one quantum of energy. And any linear combination of a one dagger, the raising operator, the x direction, and y direction has the same energy, m squared plus 1. Okay. We have a SO n minus 1 invariance as a group. So you mentioned you talk about group symmetries. You have this in the perpendicular direction. This just means rotational invariance in the perpendicular subspace to the direction you're boosting in. X can be realized, we talked about it there, as a superposition of A's. Going to be very sloppy with my notation, and Y. So X and Y transform like a two-dimensional vector because the combination of them is like that. So A and B are like a linear polarization of light, or aka a photon. Now, if you have a circular polarization, what happens? You get A plus IB, let's say, acting on your ground state. There are only two linear independent polarization states, therefore it has to be massless. Is that true? Yeah. You can either do a right-handed one, as we defined over here, right? Increase the angular momentum to become 1, or you can do the left one and become -1, so there's only 2. Because there are only 2, we talked about this, it has to be massless, right? If it was 3, it would be massive, but it's not. So for a photon, it's massless. And that's what we observe. The photon is massless. Checks out. Very nice. Okay. So since okay, therefore E has to be 0. So m squared, m naught squared plus 1 has to be 0. So that means that m naught is -1. Mass squared, rest mass squared is -1. But how is that possible? How can that be? Is this wrong? Is string theory wrong? Should we just throw it out in the garbage? Well, there are actually things that people theorize called tachyons, and they say they move faster than light. But so there does exist some string theories that don't have tachyons because because of relativity. You want to say a massless particle, it can move faster than the speed of light. But okay, but he doesn't prove this. He just states this as like a fun fact. But there doesn't exist string theories such that you don't have photons. You'll always get photons, which is good. This will be observed, but we never observe tachyons. We can't. It says faster than the speed of light. That's not possible. Photons exist, tachyons don't. And we'll get back to tachyons very quickly. Just gonna give you Newton's picture of energy versus Einstein. So energy as a function of momentum for Newton is e squared over 2m. And if we take the derivative of energy with respect to p, we get p over m, which is v. For Einstein, it's going to be E equals p squared plus m squared, right? The derivative with respect to p is going to be what? P over square root of p squared plus m squared. This is always less than 1, right? You can convince yourself of that. So if that m squared is negative, this becomes negative, right? If that's negative, then this whole thing is more than 1. It's faster than the speed of light. So having tachyons in your theory doesn't mean that it's traveling faster than light. It means it actually means that your ground state is not stable. Okay, what does that mean? So now we're going to talk about what it means for the ground state to not be stable. Okay, you'll quickly finish with the tachyons. Okay, then we'll get into strings interacting, and that's definitely something you guys probably want to see. Get rid of this. Feel free to ask any questions if you have any. So the prerequisites for string theory would be first you need to learn QFT very properly, and probably take your course on particle physics and the standard model, just to see how everything plays out, and definitely know GR very well, and then you can kind of get into the string theory. So it's our two great descriptions are QFT and GR, and that's what we're trying to unify for our grand unifying theory of quantum gravity. So those are the prerequisites for string theory. And the math, you either take a course in grad school on string theory, or you self-study it, or read a book about it. Yeah. Yeah. And depending on how intense and modern you want your string theory to be, you definitely will need more math. This is a very beginning string theory, early string theory. So the math is quite simple. Okay. Quickly, we have the wave equation because we were talking about waves. We got the energy of a wave. It's you've seen the wave equation before. This is omega squared. This is k squared. Right. And the speed of this is equal to d omega k is 1. This is just some wave stuff. Now, if it's a massive field, what do you get? You just get a mass term here. And this is the Klein-Gordon equation that you all know and love from quantum field theory. If phi is e to the minus I omega t, what do you get? You plug this in here, and what you get is minus m squared minus k squared is minus omega squared. Very nice. Now, almost at the end of that. Okay. Now, what about the energy? This is the Klein-Gordon equation. This is the equation of motion. And holy schmoly, I'm running out of chalk. That's crazy. The energy for this, so the Hamiltonian is just half time derivative of your scalar field squared plus gradient phi squared and plus m phi squared. This is the energy Hamiltonian, the Klein-Gordon Hamiltonian. Now, okay, let's look at this. If m is positive, this gives you a parabola, right? This is just a simple parabola, very easy, right? But if m is negative, sorry, m squared, that's a typo in my notes, that should be m squared. You get this. Okay, what is this? Energy is a function of your field. You've probably seen this classical mechanics. This is an unstable equilibrium, the equilibrium here when the gradient is 0. What does that correspond to? If you have a ball on top of a hill, you give it the slightest push, it falls down. So this is an instability in your vacuum. This is like the vacuum solution. Imagine this. You have a bunch of pendulums such that they're connected with springs. And if you take all these pendulums, they're upside down. Well, I guess right side up, sorry. You take them and you push all of them down, they just go down together. But if I take one of this and I give it, this is aligned perfectly vertically, so it won't fall. But if I give it the slightest nudge, it'll fall down. So if I do that to one of them, it'll start falling down. But now there are springs in between them. So there's a propagation of information that one of is falling down, and that will pull the neighboring particles down with it as well. And this will propagate. What is the speed of propagation? It's c, right? The speed of light. How fast information can travel. So tachyons doesn't contradict special relativity. It just says that your vacuum is unstable, which is also really bad, and we want to avoid that. So here's where you enter superstring theory. And apparently that fixes it. But that apparently comes way later in the lectures, and I haven't gone there, but Susskind said it does. So I'm going to take his word for it. Great, we're done with this, done with calculus. So we need to revise our theory, make it better, but at least it doesn't contradict SR immediately. But whereas there's a problem with the vacuum, which is still bad, but not as bad as contradicting SR. So we're kind of good, kind of. You know, could be worse, could be contradicting SR, which would be way worse. So so far, these strings have been free isolated strings, moving in a direction and wiggling for themselves. Manifestations of wiggles are discrete energies and angular momentum. None of these are relativistic strings. It's all Newtonian because we boosted it a lot in a direction, so it's a very Newtonian description. So if you have two strings and they connect into one string that I drew for you before I erased it, there's a probability that these two will join, and it's a probability amplitude, and it's called the string coupling constant. I'm not going to write this down for the sake of time, but also strings move and they can pass each other like this. They can pass each other, and the fact so it's actually probability amplitude per unit time. So the more time they spend close to each other, there's a high probability of them connecting, interacting, becoming like one string. Yeah, that's what I wanted to say. Is the higher the string coupling constant, the more there's a probability of them interacting and turning into one string if there are two free strings. Very nice. Now, you remember when we were talking about Feynman diagrams, this draw an electron and it interacts with the graviton? Sorry, with the photon. Gravitons are later. And so it changes the direction of your electron. This is an example. In string theory, because everything's are strings, now we'll get this shape instead, which is a pair of pants. Now, there's something really interesting here is happening. In your regular particle physics Feynman diagrams, your interaction is happening at a point. Is that really physical? Is that actually what's happening? Here, it's actually smeared out, and it's not clear when the interaction is happening and when your strings are becoming one string. But you might say, okay, what are you talking about? Time is going this way, and I have this string here, right? And this string here. And obviously, they become one string at this point, right? At this point in the pants, right? So topological space is homeomorphic to pants. And what if I boost my axes and go into a reference frame, start moving relative to it, and time becomes tilted, such that my strings are not like that anymore, and they become like this, like that. In this frame, well, am I doing this properly? Wait a second. Sorry, give me a second. Right, 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 right. Yeah. Okay. Sure. Yeah. So you have this, and you boost into a frame that your strings are now tilted in your space-time manifold that you have, and Now you say, oh, now they join and become one particle. They interact into one at a different time from here. Here it was here this time, but here now it's a different time. Okay, so what happens here? It means that it's a frame-dependent thing when they interact and turn into a one particle in the string theory description versus the Feynman diagram picture. By the tilting, you can fit it differently in your new world sheets that you have. These are called world sheets. A particle, the path it traverses in your space-time manifold is called a world line because it's a zero-dimensional point, but it moves in time, in space-time. It traces out a curve, a one-dimensional curve, which is called the world line. So in string theory, now because it's a one-dimensional manifold instead of a zero-dimensional one, it moves in space-time manifold. It traces out a two-dimensional submanifold, which is called the world sheet. Yeah. And so if quantum mechanics is reversible or ignoring collapse of the wave function, is if two strings become one, then a string can break up into two strings. For reasons that Susskind doesn't really talk about. We don't want this to happen, so we assume that the probability, the string coupling constant is small. Yeah. Yeah. But a string doesn't know any better. It can interact with itself and create something like this. Can this happen? Yes. Yes, it definitely can. So this is inevitable. This will always happen. If strings can couple to each other. So let's view closed strings. So far we talked about open strings. For closed strings, what happens if they interact? You have two closed strings like this, and this is the 0th point, sigma equals to 0, and you have another one, and they interact. So what happens is that this gets erased, and you create one closed string. Two closed strings become one closed string. So if you have open strings, that means that you'll have closed strings in your string theory. But if you have closed strings, it doesn't necessarily mean you'll have open strings. Closed strings are analogous to gravity, and we'll see why later. And you can't get rid of it. And that's one of the beauties of string theory. Gravity just magically pops out of your theory, and it's hard to get rid of. So you're given gravity kind of for free. It imposes it on you, which is kind of magical. Yeah. Since closed strings can always interact, everything gravitates, which is a consequence of string theory. Let's say you have an open string and a closed string, and these become I did it. These turn into this, which is one open string. So strings can interact in this way, an open string and a closed string. And in your Feynman diagram picture, how does this look like? You have a particle, and the graviton interacts with your particle, and it changes its direction. So yeah, everything gravitates in string theory because you have closed strings. And I mentioned this. They can questions. There's a probability amplitude of that happening. So they have to interact with each other, and the more time they spend like at the same position in space-time, the more likely they'll interact and couple in that way. What do you mean by covariance? Not for X and Y, for them to couple to each other. Yeah. So this can happen. Doesn't mean it will happen. There's a probability of this happening.
You know the functions.
Oh. No. He doesn't write that out. But yeah. Okay. Almost done. Okay. Lecture 4, last lecture. This one's shorter. Talked about strings. Now, let's quickly review Noether's theorem because we're going to use it for symmetries. You've probably seen it in classical mechanics. Very important theorem in fundamental theoretical physics. This says if you have symmetries, you have conserved quantities. Conserved quantities are generators of symmetries. It's an if and only if statement. So if you have a Lagrangian, which is a function of Q and Q dot, you define the moment as we did before as the partial derivative of your Lagrangian with respect to the velocity. So a small change in position is written as a function of your position times some small multiplied by some small quantity omega, and there's a conserved quantity called the Noether charge, which is equal to, sorry, yes. This is just a reminder defined as Qi dot L. And this is going to be sum over I, P, I, F, I, Q. And this is Noether's theorem. This is the conserved quantity, the Noether charge. And it's related to the momentum, which is defined by just having velocities. Take derivatives of your Lagrangian, so you just need a Lagrangian. This gives you symmetry. It tells you about the symmetries of your Lagrangian. And yeah. And this is how your position changes. So you have a closed string, right? It's a one-dimensional manifold. This is a sigma equals 0. This is like sigma is pi over 2 and the rest and 2 pi. So we used to, no, sorry, this is pi. So our parameterization for closed strings is different. It's from 0 to 2 pi instead of 0 to pi, just convention. Now, you do an embedding on, let's say, R2. So this is a manifold itself, but you do a topological embedding in, let's say, R2. This is Y and X. And strings are given orientation. This is 0. This is sigma pi over 2. So the orientation is this way. As an orientation. Well, it's a one-dimensional manifold, so I shouldn't do this as an area, but like this, like one simplex. But it doesn't mean that it'll preserve the embeddings don't preserve orientation. If I have this is my closed string. I want to embed it into R2. So I would take this and I snap it on here. Right? You have a rubber band, you take it, you slap it onto the board. You can twist it, then slap it on, right? So it doesn't preserve your orientation in the sense of if you look at it on the board, it's rotating clockwise and does it have to stay clockwise, right? This is an abstract manifold of itself, and an embedding can, so this is the 0, the sigma equals 0, and this is pi over 2, right? So the orientation is this way. Okay, for open strings, waves get reflected, not conserved, and okay, sure. We talked about Neumann for open strings. You have a wave moving this way, right? reaches here, it gets reflected. So because it gets reflected, it's not conserved in time. Yeah. Can I get rid of this? Let's okay, we have some waves on our strings and they're propagating. We want to talk about how these waves move. So we're going to Fourier analyze them very quick. Say x of psi is going to be sum of in your integers e to the I n sigma. This is xn Fourier coefficients. If n is positive, it's moving to the right. If it's negative, to the left. For open strings, we got either it's sine and cosine depending on the boundary condition that we already discussed. For closed strings, we can have both. And so if I decompose this into this way, so I'm just rewriting it in this way, and you'll see why in a second. Sigma n is positive plus n is positive x minus n e to the I n sigma plus x naught. Again, x naught, as always, is the center of mass. This is moving in the to the right. The waves are propagating to the, by right I mean like, let's say clockwise. This is counterclockwise. Yeah, okay, sure. Now let's write down the Lagrangian of a string. It's going to be sum over, we already derived this previously, d sigma. It's going to be the wave energy that we had. Squared. Okay, plus the y terms. This is just for the x terms, but there are also y terms. The Hamiltonian is this, but with a plus. So I write it with a plus, make this into a Hamiltonian. And so I'm just going to rewrite this in a suggestive way. Half d tau x plus d sigma x squared plus d tau x minus d sigma x. Okay, squared. Okay, I wrote it like this. This is the energy of the left moving waves counterclockwise, and that's for the right ones. So I kind of decomposed it in the energies of if it's moving to the left or the right. Why did I do this? Well, you'll see in a second. So each of the Fourier coefficients is a harmonic oscillator. You can excite each mode of the oscillation with A and A dagger and B dagger for the y's as well. A n dagger creates a right moving wave, and so A n dagger is a raising operator that moves creates a excited state for the right moving ones. And there's also a minus n. So the sign only denotes the orientation. The dagger means it's raising, and the n is for the harmonics. Same thing we talked about. Now there's just an orientation. That's the only difference. What's the spectrum excited states of these closed strings? That's the question that we want to answer. 0 is the lowest state, is the ground state of the oscillations. To give the lowest energy excited state, we need to, with the lowest state n, what do I have here? Okay. Sure. We're going to excite it to the first state. Imagine you have a light. We're going to talk about polarization again. One way you can use circular polarization doing this. One dagger plus minus IB, one dagger on the ground state. You can excite it using this. This creates units of angular momentum. If you were just to use A or B, it wouldn't do that. It's just linear polarization. This is circular. You add angular momentum to it. And the way you can excite it to the first excited state is 4 ways. A dagger for 1 or -1. Well, 1 again is moving to the right, -1 to the spinning in the opposite direction, and also for B. B is for the Y direction, A is for the X direction. So you have 4 ways in total. Okay. Because it only has angular momentum of -1 or 1, it's massless, as we discussed previously. You will get the wrong number states, however, for higher excitations. So how do we avoid that? So is string theory incorrect? No, we'll just postulate something. What are we going to postulate? We're going to postulate that the left and right moving energies has to be equal to each other. Why are we postulating this? This actually comes from a more fundamental and more intuitive motivation that we impose on our theory that will is equivalent to what I'm saying right now. And that's the interesting theorem that I want to get to that I told you about. And we're almost there. We're almost at the finish line. Okay. So we postulate that the left and right moving energy has to be equal. Okay. So for the first excited state, you can have let's just focus on the X, forget the Y for a second, have these, right? And this doesn't satisfy that, because if you put the plus, you have one going to the right, but none going to the left, and vice versa for the -1. So this doesn't satisfy that. Okay, so this isn't physical. You can't have this. Next excitation is for energy equals 2. That's E equals 1. For the energy being equal to 2 units, what do you get? Get these different thingamajigs. A1 plus, wait, A1 plus, A minus 1 plus. You're exciting it twice. So you do get E is, I'm going to drop the ground state so you guys know. You get energy is 2 units. That's good. Are the direct orientations, do they add up? Yeah, one in the negative orientation, one in the positive one. Yeah, it satisfies that. Great. Same for the B, I'm just not going to write that down. So this satisfies it. You know what? Also write it down for this. Same thing here, same logic. A1, B -1. You're exciting it twice, right? Raising it twice, energy is units 2, and there's one to the right, one to the left, cancels out, orientations. So this is also, it satisfies it, very nice. What about this, -1? B1, same thing here, same logic, checks out, good. What about this? No, right? Because you get twice in the clockwise direction, so no. You get 0 in the counterclockwise. So this also doesn't work. Not good, not physical. Same with the B's as well. Okay. Now these are for the linear polarizations. Now let's look at the circular ones. Plus. This. What's the spin on this? Well, okay. Does it have energy 2? Yes. If you expand this out, you get 2 raising operators. So yeah, energy 2, yeah. What about the spin? Well, Um, this one is to the right, this one's to the left. Is that correct? No, sorry. Sorry, that's for the energy propagation. Sure. It does satisfy this. One to the right, one to the left. Good. It does satisfy that. Now, what about the spin? Okay, this one adds a spin, a positive spin. And this is also positive because pluses, right? So the spin of this denoted as M, I know it's confusing. We have so many M's, is 2. Good. Very nice. Now, what about this? Just to check, actually, I'll do it. So energy propagation, +1, -1 equal good. Energy, what's the energy? This raises it twice, so 2 good. And what about the spin? This is minus, so -2. Ah, interesting. Very good, very good. But we're not done. There's still more ways of producing other stuff, making products. So A1 plus minus AB plus 1 minus we're almost done. Oh, almost done. A A1 plus A minus 1 plus. Aha. Okay. What about these? I'll leave it to for you to check. I'm just gonna the rest of the stuff. Just the spin. It's gonna be what? +1 plus negative. Spin is 0. But a negative plus spin is 0. For both of these, spin is 0.
I'm burned out right now.
Thanks for coming. See you. We got spin 0 in our theory, but we said for a massless particle, we're not supposed to get that. We're only supposed to get the max and min. So we're only supposed to get the first two. So what are these? Is string theory wrong? No. So for energy equals 2 units, we must have 5 states, but we have 4 unless it's massless. So for the massless case, we should only get the +2, -2, right? If it's massive, it has to be 5. This is if it's massless, we only need these 2. But this is neither of them. This is 4 states. If m is equal to 0, one is we call it a dilaton, and the other one is an axion, just names that we gave them. And we haven't observed either one of these. You can get rid of them, but you can get rid of these, but you can't get rid of these. And that's a good thing because that's what we want from our theory. And this is only 4 more lines. We're done. Yeah, what's that? Very nice. Okay. Page 13. Okay, quickly erase this. Leave that there. Okay. Why would we postulate that the energy propagation in the plus and negative direction, right, left, counterclockwise, clockwise, has to be equal, like the +1 equal to the -1. Well, let's talk about the symmetries of our theory. So if I have a string, a closed string, Sigma equals 0. Is this a special point? Or could have I picked the origin to be somewhere else? Any guesses? It's a 50-50 chance. Just guess something. Is it special? Is that point special in my closed string? If you have a rubber band, is a special one? No, exactly. Why would it be special? So okay. If I have a wave function on this string, right, closed string, it's a function of the positions. So let's take this to be discrete for an instance. X1 is a point, X2 is a point, and so on, so forth. So it's a function of this. I want this to be, I'm imposing this symmetry, which is, I think, a very reasonable symmetry that this point isn't a special point. You can pick any point to be your origin. So shift invariance, shifting of sigma invariant. So it should be equal to this. I just permute my x's, and it shouldn't matter. The wave function on the string of the strings should still be the same thing. Should be equal, right? Good. So better written as function of psi is if I shift it, I shift my sigma by some amount, it should be equal to that. So if I rearrange this, well, this minus that, the plus minus, this should be 0. Okay. Now I take this into the continuum limit because this was discrete. The integral of derivative of psi with respect to x, parameterized by sigma, times. Okay, this is just the chain. I'm just doing the chain. So convince yourself of this sigma, and times epsilon. Sigma is going to be 0. And the continuum limit, I'm just doing a chain rule, integrating over the whole sigma. I want that to be basically, it says that it's invariant. Now, you know from quantum mechanics that P is minus IH bar gradient. H bar is 1. Rewrite this. What is this? This is a gradient. So this is just P. And what is P? P is velocity. It's x dot. So I can write this. I can write that if this equal is coming from here. I can write that as just a time derivative now, because this momentum. This is a gradient. Quantum mechanics tells me, oh, that's the gradient is momentum. Momentum is x dot with where the m is absorbed, and x dot is exactly this by definition. If this stays the same, holy schmoly. This is equivalent of saying it's the sigma shift invariant. And okay, the same way I wrote the energy propagation in a suggestive way, I'll do that here. Consider this. This was energy. The Gaussian is going to be that with a minus sign. Right? Now, if I take that and expand it, it's the same thing as that. It's equal to that. And you can check for yourself, it's just like some squared. you expand it and you get that. So this is the energy that we have there. That I said, oh, let me write this in this suggestive manner that you get energy propagating to the left and the right. This is the same thing as that. If you impose the symmetry, the shifting symmetry of sigma on your string, saying there's no special points, you get that for free. These are equivalent. So that postulate that I gave you that, oh, the energy propagation to the left and to the right have to be equal, just it doesn't just come out of nowhere. It comes because there are no special points. And that's remarkable. So you get that just by imposing this. And this is an if and only if statement. It throws away the spectrum. It also, this is it throws away the spectrum you can't fit in the angular momentum integers for closed strings. And this basically is the end of it. The rest was a bunch of stuff I wanted to talk, no writing. I just wanted to say, are strings fundamental? Are things made out of strings? Any guesses?
Well, string theory postulates that strings are fundamental.
Yeah.
But are they?
So that begs the question, what is fundamental? So, and this is philosophical. So I just left the philosophical part for the end. What does it mean to be fundamental? Which one's fundamental? The electric charge or the monopole, the Dirac monopole? Well, the answer is it's whichever is more useful for you. For instance, if you have, I said no writing, but it's just like one line. Look, this is the electric charge, this is the monopole, you want it to be 2 pi for reasons, doesn't matter. And which one's fundamental? Well, if the electric charge is big, you can't do quantum electrodynamics because you get divergences. If it's small, you can do that, but in return, your Q is big and vice versa. So if you want to do quantum electrodynamics, you got to pick whichever is small so you don't get divergences. Sometimes it's this, sometimes it's that, but which one do you pick as fundamental? The answer is whichever is useful for your description. If one of these is large and you pick that to be fundamental and you draw your Feynman diagrams, you'll get divergences that it doesn't make sense. So fundamental is whichever you choose it to be fundamental based on how useful it is, and the rest of the stuff comes from that. And you can pick whatever you want, because at the beginning, when philosophers were doing physics, like during Aristotle's time, they were focused on, oh, what's the fundamental stuff that things are made of, matter is made of. But now we kind of realize that it's arbitrary. It's whichever is useful for you. Pick that to be your fundamental thing, and then you get the stuff from that. So for instance, strings could be fundamental, or something called D-branes can be fundamental, which is something that you study in M theory. And it turns out M theory is a type of string theory. And whether strings or D-branes are fundamental, whatever that is, again, it's whichever is useful for you. And this is the end of the Susskind lectures. The only few last words I wanted to say: why is string theory useful? Why should we study string theory? One, it's mathematically beautiful. If you like math, you'll probably like string theory. You get gravity for free, and it's hard to get rid of. It pops out kind of magically in your theory. The gravity pops out magically, and you can't get rid of it. So it's going to impose on you, and that's kind of magical in a way. But unfortunately, so many probability, so many of the possibilities are not testable. It's not a falsifiable theory. So is it really physics, or it might be just math? Okay, but what are some of the good things? You don't get black holes when describing gravity on small scales, which is a good thing. You don't get infinities in your Feynman diagram. Like if you have a thing like this, you might get extra interactions like that. Whatever, well, that's not correct, but you can get for strong, for a twin length thing, you can get divergences. But if you have the pair of pants, you get rid of these divergences. So you're smearing out to get rid of those divergences. And this goes back to the initial idea when we were talking about Feynman diagrams and smearing stuff out. The rest of that, it's easy to quantize. That's a good thing because we're talking about harmonic oscillators and we know how to do that really well. Dirac did a very similar thing, as in he let the math take him where the math took him, which was the Dirac equation, and then he interpreted the math, and we're kind of doing the same thing. He got a description of antimatter from his equation, which was math, and so yeah, string theory might be doing the same thing Dirac did. This is not important. So you've probably heard string theory. Well, we talked about it. Strings are one-dimensional manifolds. The worldsheet is a two-dimensional manifold. This can be embedded in higher dimensions. Actually, it ends up being in 9+1 dimensions of spacetime. But where are these extra dimensions? Are these physical? Well, people say that these dimensions might be curled up in things called Calabi-Yau manifolds. Doesn't matter what they are, but what's the idea of compactification? Imagine you have a wire and there's an ant on the wire. For us, the wire looks one-dimensional, but for the ant can also move in this direction too. So for us, it's one-dimensional, the wire, but for the ant living on the wire, it's two-dimensional. So these dimensions can be very small curled up dimensions. The same thing could happen for string theory. People say, oh, okay, but maybe like one extra dimension is still crazy, but like maybe it's true, but like, oh, 9+1, 10+1 dimension, 25+1 dimensional stuff is crazy. In my opinion, this is my opinion, I think it's the same amount of crazy. If you add even one more dimension and your reason is that it can be compactified, it goes for all the dimensions. It's the same amount of craziness, as long as it's countable and finite. But yeah, I think it's the same amount of craziness, whether it's 9+1 or 25+1. There's also something called supersymmetry we haven't talked about, but yeah, that may be good for a part 2 of this talk. We seem to not have discovered supersymmetry or the extra dimensions. So string theory might be the wrong theory, might be the correct theory for a different universe, but not our universe. So research is still being done in fundamental theoretical physics for finding the grand unifying theory. String theory has given birth to stuff called the holographic principle and ADS-CFT. What is ADS-CFT? It uses the same idea as we have a like 3+1 dimensional bulk theory, and we describe it with the 2+1 dimensional theory on the boundary, which happens to be a quantum field theory. The quantum field theory gives us a description of quantum gravity, but the CFT on the boundary seems to correspond to an anti-de Sitter space-time in the bulk, but our universe is a de Sitter space-time, so it seems that that's also not a correct description of our reality. And yeah, research is still being done. There are other ways of finding the grand unifying theory of fundamental physics. none of them have been very successful, and we're still searching. So I guess that concludes my talk. Thank you everyone for staying until 17 p.m. Sorry to take up your Friday night's time. I hope you enjoyed it. I hope you got something out of it, or at least enjoyed it. Do you have any questions? Like you have a question?
No,
No, you don't. All right. I guess that concludes the talk. Thank you. I appreciate it.
Um, well, thank you for providing like
Yeah, no worries.
content.